Every day, the sun provides an amount of energy to Earth equal to 100 million atomic bombs. However, that is distributed over the entire surface area of the planet. So if we take a look at a single ecosystem, it's going to have a defined amount of space. Here I've drawn an island floating out in the middle of the ocean. Let's assume that the island has a surface area of 1 kilometer squared. Because the island has a finite size, the amount of energy delivered to that island on a daily basis is also going to be finite, measurable, limited. And the surface area of the island is also going to limit how many plants are on that island, so the amount of photosynthesis that can take place is also limited. In this diagram, for every 10,000 kilocalories of solar energy provided by the sun, only 1,000 kilocalories is captured by the plants. That's 10% energy capture. That's actually a generous amount because the reality is that plants only capture 1% of solar energy in the form of primary production. As producers capture solar energy, they increase in size, they grow, they make more biomass. Only the biomass is passed on to future trophic levels, so only the energy that is actually stored inside the plant material becomes available for herbivores to consume. The remainder of the energy is going to be reflected off as visible light, or it's going to be lost through inefficiencies or heat, and in total, only a small fraction of that sunlight is going to be captured by the primary producers. But that is all of the energy available to this ecosystem. Now, the 1,000 kilocalories stored inside this plant material is all the food that's available for the next trophic level, which is the primary consumers, your herbivores. As the primary consumers eat the producers, they have to store some of that energy as their own biomass. However, they can't get 100% of them. Some of that energy has to be used for the work of moving around or just keeping the body going, keeping the metabolism running strong, and some of it has to be excreted out as waste. Typically, only 5 to 20% of the total energy consumed is actually going to be stored in the biomass of these primary consumers. And again, only the biomass is available as energy for the next trophic level up. In this diagram, I'm using a 10% transfer between levels in order to keep the math nice and simple. An important implication of this stepwise decline of energy in a trophic structure is that the amount of energy available to top-level consumers is small compared with the amount of energy available to lower-level consumers. Only a tiny fraction of the energy stored by photosynthesis flows through a food chain all the way up to secondary or tertiary consumers. And that explains why top-level consumers such as lions or bears require so much geographic territory. It takes a lot of vegetation to support trophic levels so many steps removed from these photosynthetic primary producers. By the time we move up from our primary consumer herbivore, the goat, up to our secondary consumer carnivore, this bear, there's only 10 kilocalories left for the bear to add to its own biomass from the original 10,000 provided to this island by the sun. But wait, I hear you say, there's no way that 10 calories is enough for a bear to live on. I need 2,000 calories and I'm much smaller than a bear. And you're correct. The number of trophic levels that an ecosystem can support is related to how much primary production it has. Since this is such a small island, we couldn't sustain a bear population. If we wanted to feed bears, the bear would need more territory, so we would probably need several islands worth of plants in order to get enough energy up to the bear, up to the secondary consumer. This fact is related to another concept I'll talk about later, which is when humans eat vegetables, we are behaving as primary consumers, and when we eat meat, we are behaving as secondary consumers. And when we behave as secondary consumers, it requires more land area in order to support that diet. Now that might not sound so bad, but the reality is that one of the driving factors of habitat destruction across the planet is the clearing of land to make more space for ranches and farms in order to grow food for more livestock, and then more prairie for livestock to be able to move around on. We'll talk more about those types of effects a little bit later on in this unit.